Hello everyone, my name is Szilvia Lestyan and I'm going to present our paper titled In Search of Lost Utility Private Location Data, which is a work done together with my advisors Gergely and Gergely Biczok. So, our problem is based on location data. About location data, the only thing you have to think about now is just GPS coordinates and timestamps and a time series that you can get out of it. So like traces when you go from one point to another, and then the locations in between. So inherently, it's very hard to publish because it's sensitive, and even us researchers, we struggle with publishing this kind of data sets, and it has had problems in the past. And even though I heard people complaining about it quite a lot. So we can't publish it because if it's just naively identified, identification is easy and anonymization is hard. I'm going to show you why it is hard, and I'm also going to show you our solution given to this problem, our model, which is more scalable than previous methods, gives better utility, and most importantly, it includes time information, and we call it DP lock. Okay, so why re-identification easy? There has been several works before. However, I think the most prominent one is this one on the screen, which shows that in a large data set of 1.5 million users, it's still possible to uniquely re-identify 95% of them using side information. So it's easy to re-identify people, but it's very hard. It's also because it's very hard to use formal methods because of cursive dimensionality. So the larger your input space is, the more problematic it is to introduce noise to your data set. And yes, originally we know that ad hoc methods don't give any formal guarantee. So this is what happens. This happens. The re-identification happens after ad hoc methods quite often, and you can't guarantee anything. So there is a solution of generating synthetic data in a privacy-preserving way. So, for example, with differential privacy guarantee, because it gives you a formal guarantee. Okay, just a very quick recap of differential privacy for those who do not really understand it. Just remember that the first line on the slide, the outcome of the anonymization scheme should be more or less independent of the value of a single record. Okay, so we hide specific user-specific information and it gives us a formal guarantee and a worst-case guarantee. Okay, so previous methods, as I mentioned, were not always scalable. Sometimes yes, sometimes not. Usually give low utility in metrics that we use the same metrics in the paper as previous papers suggested, in order to compare them. And our method gave higher, better utility. But I think that the most important is that previous methods didn't really generate realistic traces. Most of them used random walk methods, and it was very far from realistic traces. Usually, were not even long enough, and then they had an arbitrary ending. But after all this, most important is that none of them included time information, and we did include it in our model, and it did improve accuracy and utility. Okay, so a summary of our trace generation method. First, I have to just look at the first line first. You see that we have four parts, four sections. first one is dimensionality reduction. It's still a must. You still have to do it because the input of a map of a large city, the input space is thousands and thousands of cells if you put a grid over your map. So you still have to use some kind of dimensionality reduction. So we done that first, not a big deal. And then the important part here is the second step, that you take a source, a destination, and a time information from a trace. You train a variational encoder on it. So you're going to get, in the end, synthetic source, destination, and time information. So we have now this, and in the third step, we generate the transition probability between each and any location in our input space. So this is also a deep learning model with word embedding layer in it and the fully connected layer, or maybe two. The input is your current location, your destination, and the time of the day. And the output is a probability distribution over all locations in your input space. So, using the generated synthetic source destination time and the transition probability, we build a graph. It's a full graph. So, between any point, there is a probability to move from one to another. Every node, sorry. And in order to generate a trace, we have now the source and destination from the trace initializer. So we run Dijkstra's shortest path algorithm. It's a little bit tweaked in order to get the most probable path between the two locations and that has been generated by the variational autoencoder. Plus, we introduce some randomness with Metropolis Hastings, because Dijkstra is, of course, it's the deterministic algorithm. Okay, just quick one for the machine learning enthusiasts. This is our variational autoencoder. So again, source, destination, time. You generate the latent space, how it works. I'm not going to go into variational autoencoders now. And then the final layer gives you the synthetic ones. The next one is the transition probability generator. You can see that we use the embedding layer, 50-dimensional vector on locations, and we didn't embed time in the word embedding, just the location. And the output is the probability distribution between locations. Okay, so and then the last final step is, again, I show you a fully connected, a full graph, and then we run Dijkstra's shortest path with Metropolis Hastings after it. Okay, so, but this is also, it has been very nice. It was just simply synthetic data generation, but we also have to introduce differential private noise. And you have to introduce it everywhere where your model uses the original raw data. So in the first part, dimensional reduction, we use the original, we introduce some noise, it's Gaussian noise. And then the variational autoencoder and the probability, the transition probability generator models, they were both trained with DPSGD, is the differential private stochastic gradation descent. So the training of both of these algorithms are differentially private, thus using them later, the already trained algorithms going to be they're going to guarantee differential privacy. Okay, and now in the last part at the trace generation, we don't need to introduce any more noise because this part doesn't use any of the original data. Okay, we calculated the amount of noise we have to use with the moments accounted method. It's just for the enthusiasts. Okay, so what we got in the end, we could get better utility in several metrics such as trace length, visit density, source destination density, and frequent patterns. We calculated it for per hour and overall for the whole for a whole day. And of course, we cannot compare the hourly distribution to previous models which didn't use time. But even though those showed really nice results, the overall utility for a whole day without time information, it still gave better results in the majority of the cases. And below you can see just this is, I think, there's the visit density. The original, next to it R model, the AP log, and then another trace and the Ngram model's output. Okay, so what's the conclusion? So what we did again, we did synthetic location data generation with differential privacy. And we learned that anonymization with formal guarantee is hard, but machine learning methods can help. Machine learning methods like deep learning, what we used, finds specific stable user features in a high-dimensional space that it otherwise is very hard to find, and you must introduce a lot of noise otherwise. So machine learning helps, great. So what we want to reach, we want to facilitate location data sharing among scientists, among industrial people, and this COVID was like a perfect example of it. Of course, that is very hard to share data. So we hope in the future that our method will facilitate this process. Thank you very much for your attention, and I'm happy to answer any questions.